Okay, good morning, guys. So yesterday was new day for homework 5. So I want to make some comments. Let's see, it's homework 4. Um, hmm. so yeah.
What machine or six will be available for submission?
Oh, I didn't pay the Dropbox. Or
I don't see it.
yeah. Oh, okay. Thank you for letting me know. It looks like I didn't be able to create Dropbox after class. Um, but at least it's on GitHub, so
Yeah.
it's got the assignment. Okay. Okay. So in this homework, you have data set with some medical information, and the first task was to plot the distribution. Wait a second, where did I see the distribution? Okay, no. Okay. The feature importance is the last question. So the first question was just to build um, classifier, and the confusion matrix um, had a lot of, what is that? False negative. So model predicted 0, so the true class was 1. Then I asked to choose the threshold. So you could you could run a for loop to choose the threshold to get the desired accuracy. So this is how I choose this threshold. Like recall greater 0.5. And when we apply classification with this threshold, the number of what is that? True positive increased. So a little bit tricky question was to plot the area under the curve, because the area under the curve wouldn't change with comparison to the original one, because it's plotted for when we plot the receiver operating curve, we actually go through all possible thresholds. So it doesn't matter which threshold we fix for classification. To plot this curve, we go for all possible thresholds. So the curve is unchanged. Okay. And also, I want to mention that I a little bit updated lecture notes on this precision recall and receiver operation curve with additional comments. So I will show you now. Um, um, So the interpretation, I didn't mention this when we were talking about receiver rating curve. Okay, I can meet this guy. About interpretation. So let's look at two different classifiers, A1 and A2. I don't know what are the values of X. I just know the value of the model prediction A of X. And let's say I sort why they're all joining. I didn't have requests from but they won't be able to submit the paper. So if I sort this data by the output of the model, and then we have another model that when we sort the output from the second model, it provides different results for our input points X. So for example, the first model resulted in 8 for X3, and the second model gives the number 9 for point X3. So looking at these two models, what can you say? Which model looks better, the first one or the second one?
Second one gets everything right.
Yeah, the second one, because if we sort output of the model by the value of our what probability or dot product, then we can choose a threshold that actually separates our points correctly. The first model, if you look at the first, and what will be the area under the curve for this model? It will be 1, because when we calculate the true positives rate and false positive rate, then as you remember, if we choose first threshold here, we will get 1 over 4, then we'll get 2 over 4, then we'll get 3 over 4, and finally we'll get 4 over 4. So we will go along this x is the true positive up to 1, and then we will go all the way to the right. So the area will be, so the plot will be the square, and area will be 1. In this case, we have one error here, and the value for this model was 0.75. And if you calculate the number of inversions that our model performs, then so the total number of pairs, positive and negatives, will be the number of positive what's called true positive labels times the number of true negative labels, and the number of inversions when negative class was ranked higher by our model is 6, because, for example, you have this -1 inversion with this one 1, with this one 2, and with this one 3, and then this number you should also provide 3 inversions, so total number of inversions 6. And the fraction will be 1/4, and 1 minus 1/4 will be 0.75. So it's another interpretation of the area under the curve, kind of the number of mistakes our model performs, the number of inversions we should provide to get the fully correct was. Okay, so I just wanted to mention this interpretation. I have forgotten to mention this last time. Okay, now the topic of our today class is decision trees. Let's see, maybe I can use lecture notes. I also should have nice slides. Not okay. So I will pass this the this. So let's start with one idea how we can combine two features. So in other words, we can create a new feature. So for example, we have one feature, the area of apartment, and another feature, the number of rooms. And we want to predict the price of apartment based on these two features. And we can set some rules for our classification model. For example, that the area, in my case here, is smaller than 800 square feet or greater. So if our apartment has smaller area, then we go along this branch. If it's greater, then we go to another branch. And then we have another decision rule, the number of rooms. For example, if the number of rooms is smaller than 3, then the price will be 100. If it's greater, 150. And for apartment with greater area, if the number of rooms is smaller than, of course, the numbers are made up, will be 150. If the number of rooms is greater than 3, it will be 200. And this is actually the regression tree. If you want to get an estimate for an apartment, you can pass the information about area and number of bedrooms for this tree. And based on these decisions and the nodes, you will get the price estimation. But you can think about this result as the combination of two features. So we kind of create a new feature, which is the combination of two. So as you remember, this is the tree structure. We have root in the top and leaves in the bottom, and the predictions are called leaves. The predictions that we get will be in the leaves. So let's so this is how it looks in scikit-learn. So it learned somehow. We will learn today how to choose the decision rule. That the first split should be done along variable x1. So along this axis. with value 0.44. And let's look at the result. So this is the first decision rule along x1 with value 0.44. So everything that is below this line will be classified as class 1. Sorry, there's mismatch with the colors because class 1 on the image has this brown color, but in the decision tree it's blue. Every point with second feature greater than this decision boundary will be classified as class 0. Then scikit-learn created another decision rule for feature 0, and the feature 0 has value negative 0.4, negative 0.4. So you remember that the first decision rule was made by green line. The second decision rule will be done by this red line, and every point with now with the first coordinate smaller than this threshold will be classified as class 0, and every point with greater value of the first component will be classified as class 1. And the same for the points above this decision boundary. Now it has value 1.4, 1.4, and every point that has the first component smaller will be classified as class 0, and with the first component greater as class 1. And here we have the predictions in the loop. So we'll talk about this criterion Gini index a little bit later. And this is the final result. If you take arbitrary point on this plane and pass through this tree, you will get this classification. Well, because we have just actually, by the way, what is the size of this tree? What is the height of this tree?
The root, it's 3. 3, no, you need to. Actually, no, the path length is actually 2. So you go through 2.
Yes.
2 inches.
Why is it so?
Because you pass through the first edge, you get to the second to the node on the first level. The 0th level is the roots, and then you pass through a second edge to get to the next node.
Yeah. Do you know the notion of decision stump? Did you hear about decision stump? Stump. Yes. So decision stump is a decision tree of size 1. And decision tree of size 1 has only one, makes only one decision. So actually, if I close the low level, I will get decision stump. By definition, it's a tree of size 1. So that's how you can figure out that if we add one more layer, it will be a tree of size 2. Okay, so this is for classification. Now let's think about regression task. I can show the image first. So this is the points, and we want to fit a curve to these points. In other words, to get a prediction for any value of x. And this is the regression task. And you can see that scikit-learn builds like pretty deep decision tree let's think about how actually explore it. Oh, by the way, what do you think? How the classification has been done in the leaves? So, for example, we have 13 points of one class here. We have 14 points of one class and 97 points of another class. So, can you guess how the final classification is done based on the number of points in the leaf? Yeah.
I guess whichever one there's more of.
Yes, just by the majority. So we have here more points of class. What are the colors? One. So that's why it will be class one. Here we have more points of class zero. That's why the prediction for every point, maybe incorrect prediction, but every point in this area will be classified as class zero. So, okay, let's look at the regression. So let's say we have several points with values x and y. X, y. And we want to use decision tree to get the value at arbitrary point x. So let's think about how we can build, for example, a decision sum, the tree of depth 1. So we can choose just two possible decision thresholds between x1, x2, and between x2 and x3, because these are our features. In the regression task, in this case, we have just one-dimensional features. So we can build a decision tree based on different features, like in previous case. We always will set a threshold just for x. So, for example, if I choose, so just intuitively, what do you think? Where should I choose threshold? Between x1 and x2 or between x2 and x3? Which points looks like closer that they have pretty the same value of y? Which points you would group to one value? X2 and x3. Yeah, that's later we will actually solve these problems, and there's a rule how to choose this threshold based on some criterion. But for now, we can just do this by observation and choose the threshold between x2 and x3. So then, what will be the prediction for every point with x smaller than our threshold? What do you think? We have y1, we have y2. How to, well, the prediction for points greater than threshold, of course, will be y3. So our function f of x will have value y3 for x greater than threshold. But because there's just one point, but how to assign the value to our function for small x? Yes, Jonathan, you can speak without raising hand.
You state that, X, that if X is less than the threshold, then it must be another class, or maybe other classes.
Well, now it's not class, now it's regression. I want to, for example, for this point, x, new, I want to get the value of function. In this case, it will be the same as y3. So for every point here, the value of my function y will be y3. But what will be the value for x smaller? Yeah, you can speak. Yeah, it's a good idea. It's not always the case, but if we will minimize MSE, then it will be average. So it's a good suggestion to take the average. And so it will be y1 plus y2 divided by 2. For every point x, again, it's just one decision rule, just the tree of depth 1. Over 2 for x smaller than threshold. Sorry for my writing. So the final curve in quotes will look like this. So this is the first approximation of our regression task. Now let's go back to scikit-learn example. If we build like more thresholds between so like here we have much more than 3 points, and we will I'm not sure. Sometimes in the lift we can have just 1 point, so that's why we have these outliers. But for like every path in this tree, we will get a different prediction in the lift, and this is how this red curve is actually obtained. And we will do this in our problem solvents right now, because now we're ready to do problem solvings. Oh, no, wait a second. Okay, I have some more to cover. So how to choose now, how to choose this threshold? So let's look at this example. Now we're going back to classification. We have 3 classes. And let's think about if I split my points like this, is it a good split, or we could do better? What do you think?
Not very helpful because you end up with the same proportion that you start with, which
Yes. So let's look at another option. I don't want to show the next one. So what if we split like this? Is it a good split or not? Or what? What is the better split? To get the same color in one leaf. So maybe this split looks better.
I hope you agree with.
So and the mathematical formulation, which split is better, is called entropy. So you remember, entropy is the expected value of the information. So we can just, for example, for this node, we have just one class, and probability will be 1. So entropy will be 0. And so this is the smallest entropy split. So let's calculate, it's also called impurity. Let's calculate the entropy for the parent node and children. The goal is to minimize the entropy of the previous node. In this case, the entropy for parent node and for children will be the same because the proportions, as Griffin mentioned, are the same. And this is how we can calculate this. You remember, entropy is negative, the probability of the first class times log of this probability, then plus probability of the second class plus log, and so on. So it's about 1. For the second split, yeah, and the same probability for children. So for the second split, this is the entropy of the, what it's called, impurity for the parent class. This is entropy for the left class, because we have 2/5 of one color, 2/5 of another, and 1/5. And because there is one class, we have 0 entropy for the second. So it's a better split because the sum of entropies for children is smaller than the entropy for parent. But for this split, the third one, we get better values because now the entropy of the first left class, the probabilities are 1/2 for every class. So the value is smaller. So you can try all the combinations and choose the result with smaller entropy. And this is how we choose our threshold. But it's not the end of the story, because if you look at this classification, what do you think? Is it a good classification or not? Huh? No, yeah, it's kind of we didn't split our points well. But if you calculate the entropy for this split, so we have 11 points in the left node, the entropy will be 0.7 and 0 for the right node. If we look at this split, what do you think? Is the split better than previous one when we just had one green point here and the rest? It's better. But if you calculate the entropy, let's see, it will be greater because now we have 0.45 for both nodes, and the sum will be 0.9, which is greater than entropy, the total entropy in the previous case. So we should add one more ingredient in our impurity formula, which takes into account the number of points in each class, like balance. And this formula is called impurity. Pure quality or impurity we add this fraction, the number of points in left class and the proportion of points in the right class. So this is the final formula, because now these fractions will take care of the proportions. If we calculate now these values with proportions of split, then this quality for the first split will be 0.6 and quality for the second split will be smaller. Okay, just last comment about this formula. We want to reduce the entropy with our splits. In other words, we want to look at the difference of the entropy in the parent node and the entropy in children. And we want to maximize this gap. That's why this difference we want to maximize. But because we can't do anything with parent node, you can say anything against your parents as well, I think. So it's a constant. It's a constant. And to maximize this gap, it's the same as make the second term as small as possible. So instead of maximizing the difference and calculating the entropy for parent node, we can minimize this quality function. So it will we will do just less computation. Okay, now we're ready to solve the problem. Oh, well, just one final comment. Because instead of entropy, we will minimize so-called Gini criterion. Entropy is, as you remember, probability times log of probability. If you plot x times log of x, the curve looks like this blue one. If you plot another curve, probability times 1 minus probability, it looks like this orange curve. And as you can see, they're very similar. But which is easier to compute? Of course, the first one. So this is called Gini criterion. And in practice, we calculate, instead of entropy, this Gini criterion. So let's start with problem 4, because problem 4 is about classification. Because we just talked about classification. So let's start with problem 4. It has to build decision stump, if I'm not mistaken, with based on the Gini criterion. Let's do it together. I will open so this difference, like entropy of the parent minus entropy of the node, sometimes also is called information gain. You may have heard about this. Oh, Cedric heard about this. You heard about this information gain. Yeah, you had this in AI class. So yeah, let's start with problem 4. So first I will sort these points by the feature, by x. So the smallest one is 0.2. Then I will write in the row because there is more space. Then 0.4. So this is x, 0.6, and 0.7 twice. Of course, this model is not model, sorry, this data set is quite kind of corrupted because for the same feature we have different labels. So it's the problem with data set, but I choose this just because we're not guaranteed to get perfect data. Labels. So now we can choose, I hope you understand that there is no reason to choose threshold like smaller than 0.2 because then all the points will end up in one node and entropy will be exactly the same as in the original data. So we will try this threshold here, 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 and here. So let's try the first threshold. So what am I asking? Decision stump. So yeah, just one threshold. X greater than 0.2. I will write here, for example, my first decision tree will be, or stump will the threshold will be X greater 0.2. And in the list, I will just list the labels, the classes. So for X smaller, for this is no, this is yes. For we have just one point in this branch no with label 1, and other labels will be in the right node. Okay, what will be the prediction in my left and right nodes? What will be the prediction? Here will be 1, and in the right node, the prediction will be based on the majority negative, because we have more points for the label 1 here. Now let's calculate the quality factor. As you remember, the quality factor we have the proportion. So in the first class, we have 1 point, and the total number of points in the parent node was 5. 1 is. And then we calculate the, instead of entropy, we use Gini criterion. So here it's easy because the probability is 1, and we multiply by 1 minus 1. You remember the formula is p times 1 minus p. And this is 0. Plus the right node, the number of points is 4. So the proportion will be 4 over 5. And which class we will calculate first, negative or positive? Which probability? Let's do negative. Negative. So probability of the negative class will be, what will be the probability of the negative class in this node? 3/4. 3/4. So we will write 3/4 times 1 minus 3/4. I hope you agree that it's easier than write 3/4 times log of 3/4. But in scikit-learn, by default, it's Gini, but you can choose criterion entropy as well. Plus Gini criterion for positive class. The probability of positive class will be 1/4. And as you can see, these numbers are this will be the same. Oh, sorry, 1/4. Because 1 minus 3/4 is 1/4. 1 minus 1/4, which is 3/4. So it will be, the first is 0, so it will be 4/5 times twice, because they are equal. 3 times 3/4 times 1/4. 4 cancel out. 2 and 4 cancel out. And we get 0.3 or 3/10. So this was the first threshold. We should do 3 more. But now you have the idea. And then based on the smallest value of this Q, actually we will choose the threshold. Does that make sense? So now we calculated this Q for this threshold. Now we should calculate for this 3. And we will decide which split to use based on the smallest value of this Q. Okay, so I will do this, and you can do this on your own. Oh, this is actually tricky because we will have kind of one positive class and one negative class in this node. But because the prediction in this right node will be 1, we have 2 negative labels and 1 positive, then I will choose here positive class, just otherwise we should group them in one node. Probability of negative class. Positive. Well, the first parameter is result in 1 because it will be 1/2 times 1/2, 1/4 no, it will be 1/2. 1/2, and 2/5 times 1/2 will be 1/5. The first. And here again, these numbers are equal, so I will use 2. So 3 will cancel out. And to use the common denominator, we will multiply the first fraction by 3. So we will get here, 4 plus 3 to 7/15, if I'm not mistaken. And if we want to compare with our previous number, which is 3/10 or 9/30, and this is 14/30, we see that the previous split is better. But we should calculate 2 more. So could you tell me, please, do I need, let's see. Yeah, do I need to calculate the second threshold? Or maybe you can see that this split and this split will result in exactly the same quality factor, because we will have like 1 positive, 1 negative. If we use this threshold, we have 1 positive, 1 negative. So this threshold will be the same. So let's calculate. So it's the same as for x greater 0.6. So what about 0.7? The last threshold. Oh, actually, wait a second. There is no threshold 0.7. We're done. Sorry. We don't use this threshold because we can't separate the feature. Yep.
That's real quick. For the equation for Q on the x greater than 0.4, why is it ending in the 1/3 times 1 minus 2/3? Look at the prior equation that says 1/4 minus 1 minus 1/4, so it should be 1/3 minus, or 1/3 times 1 minus 1/3.
Here.
Yeah.
You're right. You're correct. But in my further calculations, I used 1/4 times 2/3. You're correct. Thank you for this.
Okay, I got something.
Thank you. Yes, thank you for this correction. Yes, of course it should be the same as here, but flipped. So 2/3 times 1/3, and here 1/3 times 2/3. Yes. Okay, so problem 4 solved, and the answer is that this is the best split. So the first threshold resulted in the best split. So this is the answer. So this is the decision stamp for this toy data. Okay, now let's go to the first problem and do regression tree. This was classification tree. Now let's go to regression tree. And I hope you now appreciate the computers, because you don't need to do to build this decision trees manually, computer will go for all possible threshold. But this is actually has the opposite side. When you will do homework on decision trees and random forests, it will take a lot of time to run because it will choose the best split. If you have several features, you should go through all possible thresholds for one feature, through all possible thresholds for another feature, and choose not only the threshold, but also the feature that you want to split on. You remember in our first example from Cyclone, it chose feature 1. So it actually tried to all thresholds for feature 0, for feature 1, and decision tree based on feature 0, feature 1 was better. So that's why the first split was done by feature 1. Okay. Now, what is the data? The data is here, 4 points. And there are 3 possible thresholds, but with maybe one more example, you actually will understand just by looking at the data which threshold is better. So, I mean, for now, we will go through kind of all possible thresholds. But in problem 1, I asked to try only 2 thresholds, greater than 1 and greater than 2. Okay, let's do that. So greater than 1. Which numbers I have here? Which predictions? 0 and 1. So numbers, the y values 4 and 5. And x greater than 1, the y values will be 6 and 100. I can write also for x greater 2, we will have 4, 5, 6. And 100. Okay, what will be the predictions? If we use, here I'm saying that we use well, actually, we won't use 1 over n. So we kind of use MSE loss, but without division by n, because if we use later this fraction, the number of points in left class is exactly the same as the denominator here, and they will cancel out. So we will use unnormalized sum of squared residuals. So it's the same as SSR. Okay. So what, and actually, I will explain later why, if we use this loss function here, the prediction in the leaf will be average. So what will be the prediction in my leaf with values 4 and 5? It will be average, 4.5. What will be the prediction in my right node? 53, yes. 53. Now let's calculate the quality factor for this first split. The number of points in the first node is 2. The total number of points 4. And here I will write just the sum of squared residuals, because if I would write M as E, I would have here 1 over 2 and 2 would cancel out. So these additional terms, the fraction of the class would just cancel out. Okay, so MSE without normalization will be 4 minus prediction squared. Yeah, why actually we learn decision trees? Because we want to learn the algorithm which is called a random forest. And first we should build trees and then we can build a forest. And the final algorithm that we will cover before neural networks is called gradient boosting. And this algorithm, gradient boosting, is built typically on the trees also. You can use any models in gradient boosting, but in implementations, XGBoost or light boost, they all use extreme trees or light trees. So that's why we spend time today to understand how we can build trees for classification or now for regression. Okay. And 5 minus prediction. Plus the right node. And again, in this case, because we have just 2 values, you can see that this will be the same as that. So 1/2 squared plus 1/2 squared. And the same will be for the next pair, because 6 minus 33 is the same as 100 minus 33 squared. And you don't need to calculate the precise number. You will see just right now that this value will be pretty high. So I even wouldn't calculate the first term. The second term will be 47 squared times 2, so a very large number. And times 2 will cancel out. 2 times 2 over 4 will cancel out, so it will be 47 squared. Now let's calculate the equality factor for the second tree. What will be the prediction for in this node? 5, yeah, and in this node, 100. There's no other numbers. Okay, let's calculate quality factor for this second split. So proportion will be 3 over 4. 4 minus 5 squared. Maybe you allow me just to write the residuals. 1 squared plus 0 squared plus 1 squared. Well, technically minus 1 squared, but it's the same. Plus, what will be the sum of squared residuals for the second node? 0, 0. 100 minus 1. And it will be what? It will be 3/2, the final answer. So which quality factor is smaller? Just by observation without calculations. Of course, the second one. So we choose this split as the best one. But if you look at the data, as I mentioned before, you can just by observation understand that numbers 4, 5, 6, they kind of close to each other. And 100 is kind of, should be in a different node. Okay. Our goal is to build a tree with 3 leaves. So we should build one more split. So this is problem 2. Here we should use the best split for the from the first problem. So it will be greater than 2. And we should figure out the threshold in this second node. So here, as you remember, it's a leaf node. The prediction is 100. So for every x greater than 2, our function will return 100. But for small x, we'll make different numbers. So what are the possible thresholds? As you remember, our data is 4, 5, 6, 4, 5, 6, and x 0, 1, 2. So now we have 2 possible choices between 0, 1 and between 1 and 2. So let's try these 2 options, greater than 0, and the second option greater than 1. And you guess what? They will result in the same impurity. Again, you can see this just from there, because this split and this split, the difference between numbers will be this. And if you have, for example, 2 thresholds with the same impurity, you choose arbitrary. You choose arbitrary one. Okay, so the predictions. So x greater than 0, then if it's 0, the prediction is 4. If it's greater, the prediction is 5 or 6, and the average will be 5.5. For the second tree, we have 4 or 5 and 6. So prediction in this leaf will be 4.5. Okay, let's calculate the impurity for the first split. The proportion is 1/3. And what is the residuals? 0 for the first node, because we have just 1 line. 4 minus 4. The second node, 2/3. Here we have 2 numbers, 5 minus 5.5 squared plus 6 minus 5.5 squared. We will have 1/2 squared twice. So it will be, I'm a little bit lazy to write, but it's better to write 5 minus 5.5 squared plus 6 minus 5.5 squared. I will just write that it will be 0.5 squared twice. And the final result will be 1/3, if I'm not mistaken. For the second split, possible split, we will have 0 for the second node, for right node, and here we will get exactly the same number, because it will be, the difference will be 1/2 squared plus 1/2 squared. So it's better if you write explicitly here, like 2/3 times 4 minus 4.5 squared plus 5 minus 4.5 squared. But the result will be the same. And as I said, it's up to you which split to choose. Okay, finally we can plot this decision tree regression. So our thresholds, for example, the first three will be 2 and 0. For the second, it will be, I will draw both cases, 1 and 2. You don't need to draw two cases, just one is enough. So if I'm using the first decision tree, for x 0 and smaller, the value will be 4. So for smaller, it will be 4. For x smaller than 2 but greater than 0, the value will be 5.5. And for values greater than 2, the value will be 100, somewhere very, very high. So this is how we will plot decision tree, the prediction. So for the second tree, we will have 4.5 until 1, 4.5. And 6 between 1 and 2. And after 2, again, 100. And now you should classify what is the prediction for x 1.6. It's very easy. You just, whatever plot you are using, you just find the point 1.6 and you get the prediction. So for the first plot, y of 1.6 will be 5.5. Okay. Or 1.6 will be 5.5. For the second case, the prediction will be 6. Okay, we should stop here for today. I maybe just want to show the result. Okay, I will show the result from scikit-learn next time. Scikit-learn actually will split not by 0, it will split by 0.5. So it will be 4 until 0.5 and 5.5 after 0.5, which will take a split kind of in between. Yeah, don't forget to sign your papers, and you can leave them